I'm starting it, and we are getting into the next level to the course. I mean, we are growing a little bit in terms of analysis and understanding of the data path. But we are going to learn something more into it, and that's nothing but control signals. We are going to learn how do we use the control signals effectively, and what are all the inclusions that this control signals bring in into the entire data path. Remember, we just learned the names of the control signals the last time. We didn't think about what would be the value of it. Will it be asserted or deasserted? We didn't talk about all those in the previous couple of sessions, right? So we need to think about that, and we are going to learn more control signals now, which are going to help us out in understanding the complete data path and its functionality in a more effective manner. This is very important, so please pay attention. Now, we need to understand one very important point through this entire learning. We could have observed that the position of the opcode in any type of instruction, be it R type, be it I type or J type, it remains the same. Did we change the position? No, it is all from the last 26 to 31 bits everywhere. It is 26 to 31 bits everywhere. So this is consistent. This is one observation. The opcode field remains consistent. This remains consistent. This is one observation that you need to follow. So we observe something out of it, that we need not break our head with respect to implementing a control signal, implementing anything related to control signal for, I mean, in a different way for different instruction types. We all have different instruction types, but the opcode field remains the same. We are blessed there, and we do not have a problem there. Now, the next point that we need to understand, we can understand, and you could have observed that the position of RS and RT, they are the source registers. RS and RT, RS, RT, RS, RT. They are the source registers for all the R type instruction, load and store and branch. So there is a lot of uniformity in terms of RS and RT, and they are in the same position, and they do the same role for R type, load and store instruction, also for the branching instruction. Remember it. This is another observation that we have right now. I have got RS and RT being consistently followed everywhere in the same position, right? I mean, the position never changes. Rest of the fields, I don't worry about it. These fields are immaterial for me now. They keep changing, and we need to really work on it. Now my point is, I am observing what are all the unique, what are all the same contents over there in the rest of the instruction types and rest of the instructions. I mean, different varieties of instructions. So that's what we are observing right now. Now we need to use multiplexers at more places. That's one observation that we need to have, because I have got multiple functions to be performed in the same data path, as I told you earlier, and we need to have multiplexers to make sure that the respected required input is only sent in through this device, and this device is capable of handling these three. Any of these three can be sent out as an output. And now I'll have a control signal here that is going to rule the game. That's it. I am going to now teach you this part, which is very, very important. I'm going to spend about 15 to 20 minutes here. Please pay attention carefully. Now, you must have understood already that we have used the signals REG, right? We have used the signal ALU OP. This is new now. This signal is new. We'll talk about it. Mem write you are aware of. Mem read you are aware of. Mem to reg you know. We know what is PC SRC. This is also clear. The new signals that are included here, I mean the new inclusions in terms of this control signals are REG DST. This is very new, and here you can see that there is something called as ALU control which is added, and which is also having a control signal called as ALU up. That's it. Now what is it, sir? Very simple. The control signals are all up and running in this picture. Remember, there are two very important terms that I will keep using from here on. One is assert. Assert means it is logic high, it is 1. Another one is deassert, which means logic low, which means a device or an equipment or a component is in a logic low state. When I say it is asserted, it represents logic 1. When I say it is deasserted, it represents logic 0. Now, how does this exact stuff work? Now you can see that we have got inclusions of the signals like REG, DST and ALU op. So what is it going to do? Now remember, the new signals whatever we have included have got functions, and the ALU op is going to decide which is the ALU operation which is going to be performed. If the ALU op has got 0000, it will do AND. If it is 0001, it will do OR. If it is 0010, add. So please remember this table, and this is very, very important. This is the only thing I probably will ask you to memorize. Remember it, this is the only thing that I want you to memorize. The ALU control is done by this 4 bits, and this 4 bits decide what kind of operations will be performed, and that's determined through this bit. So please memorize it, and this is very important. Now let's get into the next level. I need to tell you how exactly each and every field is working. Now what is REG DST is nothing but register destination, right? A register destination. Which is the destination register? So when deasserted, when it is deasserted, it will take RT as the destination. When asserted, it will take RD as the destination. Remember, when deasserted, the destination register is RT, and when asserted, it will be RD. I am clearing it off again. You see that here once again. I come here and it will be RT if it is 0. It will be RD if it is 1. So 0 is called deassertion, 1 is called assertion, and remember it, this is very, very important. So this is a new multiplexer that we have in picture. This will select which register is going to be the destination register, and based on the values that we put in there, it will select either RT or RD as the destination. Now this point is clear. We have completed this right now. Now what is REG write? REG write, there is no point in talking about it being deasserted. There is no point, it is not applicable. When asserted, what will happen? Whatever register we have selected as destination will be returned with the content. So when REG write goes high, when this goes high, it will write the content, it will enable us to write the content into the selected register as per the instruction. So what is the first instruction? What is the first control signal we saw? REG DST. This will select the destination register as RT or RD. When asserted, it will be RD. When deasserted, it will be RT. Now the next signal that we have to see is the reg write. What is reg write? The name itself is very clear. Register write. So there is no point about thinking about deassertion here. Not applicable for 0. Applicable for 1. When I get it 1, we already have selected, for example, say we are writing something into the register RD. So this RD will be returned with the content that we have already ready. That's it. We have completed 2 control signals clearly. So the state of assertion and the state of deassertion are the most important components to be remembered. Now what is the next step to go with? The next step to go with is, see, I am going in a very streamlined fashion. I started with the left and I am going to the right. You can see that here I started with the left. I first completed REG DST, then I completed REG right, then I am getting into ALU SRC. What is ALU SRC? The name itself is telling it very clearly. It is nothing but the ALU source. What do you mean by that? It will enable you to send the ALU source from this input, or it will enable you to send it from this input. Let me change the color so that you can see it. All are red in color, so I think it will be a little troublesome there. Right, I have changed it now. Now it should be better. Now see that if I am going to take it from the read data 2, I mean from the register, I will go with the deassertion state. If I am going to take it as the sign extended offset input, I will go via 1. So the input to the ALU could be this, or it could come from here, as I already told you, and that is done through the signal 0 and 1. 0 will take you to the register, 1 will get you the content from the sign extension unit. That's it. So we have completed 3 things. The first one is REG DST, the second one is REG write, and the third one is ALU SRC. The complete status is all to be called as asserted or deasserted. Do not call it as set or reset, call it asserted and deasserted. That's the technical term that we need to use. Do not change it and remember it. Now what is the next one? We need to go in the same order. So I'm coming here. PCSRC is the next one to be included. PCSRC. So what is PCSRC? It tells that it determines what is the source for program counter when it is deasserted. When it is deasserted, you can see that here. When it is deasserted, it goes in a normal way and there is no problem. It is all very smooth, and this is how traditionally it gets going. Now when it is asserted, what will happen? I want it to be asserted. Then it means that there is a need for the branching to be done, and the input comes out from this after multiplication by 4, and that is the value that you need to feed in into this, and that's the one that gets in into the PC. So what are all the things that we have done here? We have taken the PCSRC, and the PCSRC gets updated with the updated input for the branching if it is asserted. If it is not asserted, it goes with the normal traditional workflow. So remember it. So we have completed 4 signals now. The first signal being REG DST, which will select the register destination. The second signal being REG write, which will enable us to write the content into the register that is destined for the return process to be completed. And ALU SRC will select the input to the ALU. I mean the second input to the ALU will be selected appropriately through the ALU SRC. Now what is memread? You can see that here memread is here and memwrite, both are highlighted here. Memread and memwrite are there. What is memread? Memread, you know that I am going to read the content from the selected or designated memory, and it will be sent back to some register. That's it. It's very simple, right? The content shall be read from the memory location which is pointed out based on the calculations that are completed in the ALU. Now there is no point in talking about 0 there. So memread on 0 is not applicable. Memread on getting 1. Memread when is enabled with 1, it means that we are going to get the reading done. The content is to be read from the memory location, and it will be made available for writing back into the available section, available area. When I want to write it somewhere, when I read it only I can write it. So this enables the reading to be completed. Now what is the next one? The next one is nothing but the memwrite. Okay sir, what is it sir? When I go with the store word instruction, I need to write the content into the memory. So 0 for this is again not applicable, none. 0 has got no action. But when I have 1 in this field, what will happen? The writing into the memory happens, and the memory address is already generated by us, and it will write the content from some register into the memory, and that's mostly is store word. So we have completed 6 of very important signals that we need to know, control signals that we need to know. The last one is nothing but mem to reg. What is it? When it is 0, you can see that when it is 0, it is nothing but the value is taken right away from this ALU and is fed into the register. When it is 1, we are reading the content from the memory and the value is fed into the register. So here it is directly taken from ALU. You can see that here I have updated. Here we take the result from ALU, and this is the spot. Here we take the result from memory. That's it. When you read the data from memory, it is going through 1. When you read the data as the result from ALU, it gets into 0 and it is written into some register. That's all. We have completed the signals and the corresponding status for assertion and deassertion clearly. It is a very important question, and there can be questions like what is the status for this operation, what is the status of this control signals for this operation, and you will have to write it. Sir, how does it work, sir? I'm going to show you that once again here. This is a bigger picture, but I have added something more to it. So we have added some more modules to it, remember it, and the module is nothing but we have added something called as control unit. Till now, is there any doubt for you? I have completed almost 30% of what I wanted to do today, so we have got more things to be done. And this is again very important. We are going to learn something more now. We have added new control signals. We have added new multiplexers into it. Now what I'm going to do is I'm going to add something called as the ALU operation, and most importantly control unit. Sir, you said all the control signals here. I mentioned all the control signals here clearly, and you can see that I have mentioned all of them here. In this picture it is more appropriate. Yeah, here you can see that I have mentioned all of them here. But where do they originate from? Here you can see that it is all blunt. It is all really blunt, right? It is not connected to anything. Nobody is controlling it. So I need a place from where all these control signals originate. I need to know from where all these are triggered, from where all these are collected together, and that is called a control unit. I need to now have a control unit. and that's what I'm going to do now. With this, I'll close for the day because it is too much actually. So I'm going to go slow, step by step. I'll explain you this and then I'll close for the day. I want you to go through it and come back tomorrow so that we can discuss more on it. Now, draw a box called as control unit. This is the box that I meant. You need to draw a box called control unit. And in the control unit, name all the control signals that you have already referred to. REG DST is there, REG write is there, ALU SRC, ALU op, mem read, mem write, mem to reg, PC SRC. That's it, right? We have ticked everything. Now what I need to do is, this control unit will have a line which has to be connected to each of them. You can see that here REG DST is connected this way and it is going to be connected to REG DST from the MUX. So it means that this control unit is the one which is going to drive this control line to control this particular MUX. Last time we did not complete it. It was incomplete. It was actually blunt. You cannot leave any control signal blunt. Remember it. The control signals are to be connected to the source appropriately. Only then it is controlled. Otherwise, it is left idle. So what I do, earlier it was left idle like this, which cannot be done that way. So I take that and I connect it to REG DST here. It is like this actually. That is what I have done. And now this is done. So what is the next control signal, sir? I have a control signal called mem read. I am going to go step by step. I will talk about this branch and ALU op in the last. I'm going to talk about these two in the last. Till then you will have to wait. Now mem read is here. It is all very simple. I'm taking it here and you can see that I connected to mem read. That's it. Mem write again I have taken it and I connected here and you can see that it comes all the way here and I connect to mem write. ALU SRC you can see that it goes here. I am connecting it to ALU SRC appropriately here. It takes a turn, long turn, but I made it short here. Similarly, PC source, I missed it, I believe. PC source comes directly, so no problem, forget it. PC source is not to be shown here, or we can add that even. That's not a problem. Now the most important point comes into picture. That's nothing but the ALU op and the branching instruction. How do we include that, sir? It's a very important thing to be done. So please remember and see how exactly we can do it. The PC source is updated here actually. You can see that I'll explain you that during the branch. That's the reason I did not update it separately. Otherwise, we may need it that way. Since the PC source has got connection with branching instructions, we need to be careful. Let's see the branch first. Now what happens? There is a signal called branch. This means there is a signal called branch which is coming and you can see that there is an AND gate. And the second input for the AND gate is coming through. You need to go all the way here and see that this is the path which is connected. Can you see that? I'll repeat the tracing so that you can understand it better. I'll do it for you once again. If you do not understand, I'll repeat it, don't worry. Now I need to draw an AND gate. One input comes from this branching signal and the second input comes from the 0 of the ALU. Why do we need that? Whenever we go for BNE or BEQ, it is all about comparing, right? Branch if equal or branch if not equal. So the result of this, and if it is a branching instruction, and if the result is as expected, if both are 1, what is it? It is an AND gate. So the output will be 1. When the output for this AND gate is 1, remember I'll repeat it again for your benefit. Please listen carefully. When the output of it is 1, you can see that it goes here all the way, and you can see that it is driven into the PCSRC, which means it will only then enable you to take up the address which is updated or the address which is going to be streamlined normally. Do you understand? So I have got a new picture here where I explained you clearly about the branching. I'll repeat how exactly branching works. The branching works with an AND gate as the basic gate. I get one input from branch which will be 1 always. I enabled that. The another input comes from ALU output. The ALU, when it is 0 or non-zero, based on what instruction you are taking, will come here and it can be fed in appropriately, and based on that I will take an output here and this output will drive your PC, which is nothing but the program counter, and based on this I will take the direct signal or I will take the modified SLL by 2 address into it, and that will be the PC source. That's all. Did you all understand this point? This is very, very important. If you cannot understand, I will repeat it even for a couple of more times so that you will understand it. Now, what is ALU op? ALU op is nothing but which operation ALU has to do. So, I have taken a signal here and I am porting it on here, and you can see that I have connected to ALU control. That's all. Now, we have got multiple signals into picture newly. What are all those? I have got the branching newly included. I have got the REG DST newly included. I have got the ALU op included. These three are new. So the question would be like this: for the given instruction, for example, add T1, add $T1, $T2, $T3. When this instruction is executed, what are all the signals that would be in the state of assertion, or what are all the signals that would be in the state of deassertion? This should be the question. You need to then scroll it through from the left to right appropriately and then tell which are all the signals which are asserted and which are all not asserted. Do you have any queries in this till now? I want you to tell me very clearly, because I am going to ask you questions only based on this in the next quiz. So do you have any questions in this? Should I explain you this again? Any questions, folks? I'll explain it once again. Now understand, the multiplexers are all governed by, you can see that there are three multiplexers here. One is here, second one is here, third is here, four is here. So what are all the multiplexers here? These four multiplexers are there, and there can be a question. Mention the names of the control signals which are governing the multiplexers. REG DST is one. REG DST, this is one. ALU SRC, this is second. ALU SRC. Then mem to reg, this is third. PC source, this is fourth. So these are all the multiplexers which are controlled by the control signals, right? So out of which I can traditionally call these three closing my eyes, but this is an input, that is PCSRC's input is coming from two things, branch and the zero output. This is the only thing that you need to remember. Now remember, the entire ALU operation is controlled by ALU op, and I have shown you a table sometime back which has revealed the matter of fact that we have got the ALU control lines as 0000, 0001, 00010. Likewise, we have got the values. Remember these values, they are the ones which are going to get you the operations done, right? So this is all done right now. Now I have explained you the purpose of AND gate clearly. That's what this slide is all about. Now this is the overall picture. I want you to go through this picture peacefully at home and then come back to me if you do not understand something out of it, so that I can clarify. Now with this I close it today. Tomorrow I'll let you know how do we draw this and how do we get these values. This is what I referred as getting the control values. It's very, 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 very important. There is no doubt, and this is very, very important. So we will have to listen to it carefully, and tomorrow I'll teach you that. I don't want to rush. I will have a lot of time for you to teach this, and then we need to understand all this. We need to then trace it. In this picture, we need to trace it then. We have traced it in the previous level before that. Now it's becoming highly complicated where we need to trace in this. And this is what will be asked in the exam, and we will understand that also very clearly. With this, I close for the day. And if you have any questions, you can ask me. Maybe you can message me also if you have any questions. We will meet you again in tomorrow's lab as well as theory. In tomorrow's lab, what I want you to do is, once again, let me complete. Tomorrow's lab, what I want you to do is, I want you to completely implement the flip-flops. I have got the code. I'll explain you. I will explain in a very simple way, like a traditional flip-flop. I'll explain you very simple way, and that will be very easy for you to understand. Tomorrow we'll have to implement that in Verilog as well during the session, and don't cut the classes. And most important point, try it out only then.